Good day, everybody. Justin Noor here, Oxnard College Physics. Today we're going to be looking at some Motional Emf. So we've discussed and looked over Faraday's law of induction. Which ultimately says that an induced EMF is a result of n turns of a conductive loop and some magnetic field flux that is changing with respect to time through that conductive loop. So what we want to do in specific is look at a nice case, what is known as motional EMF, and try to extract out some notions of inducing EMFs and inducing currents, ultimately generating electricity. So, let us do this. First, consider this. Consider that there is a conductive bar that is moving through a magnetic field. So I'm going to take ourselves a constant magnetic field. Let me do this. Consider a conductive bar. Moving through a uniform magnetic field. We'll take some little conductive bar like such, and we'll say that all over in space is this nice magnetic field. It's a uniform magnetic field. And we'll just go ahead and say that this bar is moving to the right with the velocity v hat. All right, we ask ourselves this: does anything happen? And the answer is, I hope so, otherwise what would be the point of this? So, this bar is made of what? It's made of material that has protons, electrons, and neutrons. And protons and electrons are charges, and they will be moving through this magnetic field. And we've already noted that there will be a magnetic field force on a charge that moves through a magnetic field if there is some sort of tangential component of the velocity with respect to the direction of the magnetic field. Which in this particular case, all the charges are moving that way, the magnetic field is into the board, they're perpendicular to each other. So we get there's forces on the protons and the electrons as this bar moves through this magnetic field. So the question is, does anything happen due to that force? And the answer is subtle, but it is yes, something does happen. So we have that within this bar there's conduction electrons that are free to move around when they feel some net force acting on them. And then we got the other protons and tightly bound electrons that are more localized, not able to really move around. So what happens? Well, the electrons that can move around do so. So let's think about the direction of the magnetic field force on the electrons within this bar. So bar is moving to the right. The magnetic field is into the board. The force on positive charges would be up. So the protons feel an upward force, but they're bound to their positions for the structure of the material. The electrons feel force in the opposite direction, which would be a downward. So what's going to happen? So electrons are going to shift downward and ultimately produce kind of a bunching up here. Electrons feel a downward force. Due to their motion through v hat, and they bunch up here. What does that leave? at least some exposed protons. Those electrons had to come from somewhere. When this bar wasn't moving through the magnetic field, we have a nice even distribution of the protons and the electrons. So we're left with this. At the top, there's now some exposed protons. What do we have? We've got a polarization within this bar itself. Separation, if you will, charge separation. And what do we know about charge separations? Well, there's going to be some sort of electric field associated with this. So, we're running out of colors here, but that's okay. We can go ahead and work with different blue. And we will have an electric field that points away from the positive and down towards the negative. So within this bar, get this electric field as such. So we can take that this bar has some length L, and we could start to figure out things like, hey, what's that electric field strength? And when do the electrons stop bunching up at the bottom? What prevents them all from just going down there? So we think about this. There's two forces acting on these electrons. There is a force of attraction to these protons here, and there's the magnetic field force which forced them down in the first place. When do they stop bunching up there? When the net force on them is equal to 0. When the force of attraction is equal to that force through the magnetic field. That's when they stop bunching up. And that is substantiated by a certain magnitude of an electric field and a certain velocity at which these charges are moving. So let me not say charges, let me say electrons. The electrons cease to bunch up when the magnetic field force and the electric field force acting on them are equal in magnitude. Well, what do we have with this? We've got that the magnetic field force has a magnitude of QVB sin theta. We can just write QVB because theta is going to be equal to 90 degrees here. And the magnitude of the electric field force is going to be, well, the charge of the electron multiplied by the electric field strength. So let's just put Q times E, where Q is the electron charge in general. So when those two are equal in magnitude and they are opposite direction, that is when the electrons stop bunching up, which we've seen this before. Where do we see this at? Saw it in the mass spectrometer's velocity selector. So from this, we see that by equating them, we have that V times B is equal to E. So the velocity multiplied by the magnetic field strength is equal to the electric field strength. That's when the electrons stop bunching up. But there's more to this than just this. Because we can go ahead and take this bar that now has this charge separation in it, has a length L, electrons down at the bottom, and our protons up at the top. And say, hey, that charge separation has some separation distance, which is, we'll just say it's equal to the length of the bar itself. Charge separated by the length of the bar, because really these are bunched up at the ends. So, what about the electric field? Well, if we drew in the electric field, let's draw it in again, why not? an electric field substantiates some amount of potential difference. We know that the absolute value of the potential difference across a portion in space that contains a uniform magnetic field, so we'll assume that this electric field, assume that this electric field is uniform, well, that is equal to E times L, or E times D, but D is equal to L in this case. So what do we get from this? Well, we get that E times L is equal to delta V, the potential difference between the top and the bottom of the bar. Just say potential difference across the ends of the bar. So what can we do with that? Well, we've got this relation between the electric field strength, the velocity, and the magnetic field in the system. So with this and this, I can multiply both sides by L and turn that E side into delta V. So let us write this. Since E is equal to VB and E times L is equal to delta V, we can write that delta V is equal to V times L. The potential difference that is ultimately induced across this bar by moving this bar through the magnetic field is equal to the speed of the bar, the magnetic field strength, multiplied by the length of the bar, VBL. This is an induced EMF. Pretty cool, yeah? I agree. So what we want to do with this is actually get something out of it. And what we want to get out of it is get some current out of it. Induce an actual current. Well, to induce a current, I would need to somehow connect back the negative side to the positive side. Have a completed circuit, if you will. And then we could start to get some current in there. But I have to be able to do that while keeping this bar moving through the magnetic field. So let us try to come up with some way of doing that. And then note that we didn't even look at Faraday's law of induction by deducing this. We just used things that we already knew about electric fields, magnetic fields, and the forces of interaction. So now we will consider a system in which we are sliding a bar across a bare wire that is immersed within a uniform magnetic field, and see if we can get some current out of it. Now consider that's some resistor. That's a really bad resistor. I agree. Horrible resistor. Much better. Got some resistor. Still looks a little awkward. I'll live with it. Some bare wire that's conductive, and then we'll take ourselves a nice bar. Nice conductive bar, and we will move this bar some velocity V, slide it across these wires, and we will have this whole thing immersed within a uniform magnetic field. Say, what's going to happen? The same thing that we had when we moved the bar through the magnetic field is going to happen in general. We're going to get that electrons are forced downward, and they're coming from the bar itself, which leaves sort of a positive polarization up at the top. But now we've got something special. We've got that the electrons don't just bunch up here, because they've got a pathway. They've got a pathway to take and come back up here to where they want to be with the protons. But there continues to be a force on the electrons within this bar that keeps moving them down as they cycle back around. That's a current. We get ourselves an electron current out of this. So within this bar, there's still this electric field due to a charge separation, but that charge separation continues to produce a flow of the electrons themselves. So we've got ourselves this electric field in here, and we get ourselves an electron current flowing around. So that will be the direction of the electron current. Electrons are forced down. This is what we've got going on. So let's call that electron current I sub IN. It's an induced current due to an induced EMF. Let us look at this system in terms of Faraday's law of induction, which we didn't use prior to this, and see what we can do with Faraday here. So Faraday's law of induction says, again, that if you have a change in magnetic field flux through a conductive loop, with respect to time, you will induce an EMF. And that induced EMF, if a completed loop, will go ahead and induce a current. So let us take a look at this. First off, we've got some things like area to consider here. So there's the area enclosed by the loop. The magnetic field in this particular case is uniform. It's not changing with respect to time. But as this bar slides this way, what's going to change? The area enclosed by the loop. We move the bar this way, that area gets larger and larger and larger. What does that mean? That means that there's a change in flux, because we will have, in general, for these constant cases, that the flux is equal to AB times the cosine of theta. And this is magnetic field flux. AB times the cosine of theta. B is constant. Theta is the angle between the area vector and the magnetic field vector, which is constant in this case, 0 degrees. But what's changing is changing. So for us, for our case, B is equal to a constant, theta is equal to 0 degrees, and A is changing with time. Alrighty then. So let's take a look at this. We go back up to Faraday's law of induction right here and go ahead, and what we're going to do is try to figure out what this d phi sub b dt is, the rate of change of the magnetic field flux with respect to time. So let us look at d phi sub b divided by dt. We figure out what that is, we're good. Well, we've just said that phi sub b, the flux itself, is AB times the cosine of theta. B is a constant, and theta is equal to 0 degrees. Cosine of 0 is equal to 1. So we've really got that this is d by dt of A times B. We'll write it out in a couple steps. Cosine of 0 degrees, which is equal then to d by dt of A times B, which is equal to B times d by dt of A. Again, B is a constant. The only thing changing with respect to time is A itself. So if we can figure out how the area is changing with respect to time, we can go ahead and figure out what d phi sub b dt is, and thus the induced EMF as well. So make a little room here. And come back up here just really quick and think about how this area is changing with respect to time. This bar will undergo some displacement due to its velocity, right? It'll undergo that displacement in some amount of time. So we'll say that it undergoes some displacement in some time t. What happens? Well, now the bar is over here. Which means that this now is the total area. So we added on all this additional area. The area itself is equal to the length times, let's actually say the change in area, the additional area. Call this A1 is equal to, the additional area is going to be equal to delta x multiplied by this dimension here. So let us still keep this bar having a length of L as we did before, and we will have then the new area, or excuse me, the additional area is going to be equal to L times delta x. So that's how much we've changed the area. We've changed that area in this time at delta t. So if we look at this, delta A over delta t, the change in area over the change in time is equal to L times delta x over delta t. What's delta x over delta t? Well, it defines an average or a constant velocity. So we can write this as delta A over delta t being equal to L times v. And this is either the average change of the area over that time interval or the constant change in area over that time interval if the velocity itself is constant, which it is in this case. This right here, this is dA by dt. That. So what do we end up getting? We've got ourselves that d phi sub b dt is going to be equal to b times dA dt, which is going to be b times v times L. What does Faraday's law then say? We're just going to look at the absolute value of the induced EMF and get ourselves that that induced EMF is going to be equal to NBVL. Where N is equal to 1 for a single term loop, and thus we get ourselves BVL. You go back and look at what the potential difference across the bar moving through a magnetic field is, and we got the same exact result. Same exact thing. But now we get it utilizing Faraday's law of induction. So that's nice. Give us the same results. We already really could have said this, but it's best to be able to show, right? Show Faraday's law of induction definitely does work, and well, allows us to better understand the application of it as well. The induced current. I sub in is then, I sub in is absolute value of the induced EMF divided by the resistance of the loop itself, or resistance of the resistor that we put in there, and that will then be BVL divided by R. The reason that we just take the absolute value of the induced EMF is because we're not worried about the polarization direction. We're worried about the how much potential difference, how much current. The directions of things can be substantiated utilizing Lenz's law and some other things. All right, so that's what we get out of this in terms of the motional EMF and inducing a current. Little application of this, I always like to think back to like old movies where they want to blow up some dynamite in a cave or something. And what do? They take this wire, attach it to some dynamite, and take it out and hide behind some rocks. And they've got this little system that has a plunger. It's like a box. Got a plunger, there's a box here, there's this plunger part. They go ahead and push it down and boom, the dynamite blows up. Say, how the heck did pushing that plunger down make the dynamite blow up? Well, what pushing that plunger down did was induce a current in that connected wire, which connected to some blasting caps in the dynamite, which then makes the dynamite explode at a reasonably safe distance away. So that's a operational principle there. Pretty cool, pretty cool. One last thing here regarding this. Could we just set this bar into motion and it just keeps on sliding, keeps on producing electricity, as long as there's no friction between it and the bar, no external resistive forces acting on it? Or does it take energy to actually continuously produce this electricity? And the answer should be somewhat obvious, that you're not going to get energy for free. You've got to be able to put energy in to get electrical energy out. So what we want to look at this point is what sort of oppositional force is there as we want to keep this bar moving at a constant rate. I want to keep it moving at a constant V. I have to exert a force on it to do it. It's not going to do it by itself. So why do I have to exert a force on it? What other forces do I have to overcome? So let's look at this. Keep the bar moving at a constant rate. A force must be applied to the bar in the direction of its motion. So let's look at what that force actually is. Just go ahead and draw this out really quickly. Got our bar moving here. Throw in a magnetic field. Some velocity vector. And what else do we have? We've got ourselves some applied force. We're saying that we need, which means that there must be some other force. So for the bar to move at a constant rate, the net force on it has to be equal to 0. So the question is, why do we need to keep pushing on it? So ignore any resistance in terms of friction or air resistance. Just ignore that and think about what do we got to overcome here. So we've got a current cycling around in here, and in this bar, we've got ourselves an electron current. Which then cycles all the way around, that's fine. Well, let's just consider that current in the bar. We know that there is a magnetic field force on a current carrying wire. This is like a current carrying wire right here. It's a bar, but it's just like a wire, right? So there is a magnetic field force on the bar due to the current traveling through it while immersed in the magnetic field. The magnitude of that magnetic field force will be equal to I times B times L. I is the current, B is the magnetic field that it's exerted in, and L is the section length of that wire, which is the bar in this case. So this is sort of familiar with some other stuff that we've gotten too, because we've got a lot of different things going on here. But let's think about the direction of the force exerted on the wire due to this particular current here. So direction of the current is downward. Direction of the magnetic field is into the board, which says that the direction of the magnetic field force is that way, except this is an electron current that we're considering, not the conventional current. So the force is actually in the opposite direction. The magnetic field force on this bar, due to the current within it moving through, the current through it moving downward through the magnetic field, is that way. It has this magnitude right here. The faster we move the bar, the greater amount of current that we have, but the greater amount of resistive force due to that current interacting with the magnetic field that we have. Which means that, well, if we wanted to move faster and make more current, we've got to apply a greater amount of force. That's it. So, to keep it moving at a constant rate, keep the bar moving. We must have that the magnitude of the applied force is equal to the magnitude of that magnetic field force exerted on the bar, this, which is equal to I times B times L, where I, the current, is B times V times L divided by R. So, we have the magnitude of the applied force must be equal to, we'll stick this I in for there, and we got a B squared V L squared divided by R. Lots of stuff going on. Lots of stuff indeed. A couple different interactions. That's it.